I'm just wrapping up from. You don't remember where you keep all your things from Friday? Yeah, we're going to INEA 05. All right, so you probably should all have this. INEA 05 from a shared folder that you share with Windows. There are several files that we generated last week. And last week, the last thing we did was the first stages of the Kmer analysis. Yeah, where we all got to see, we got to create a plot. Can you please all load what we've already done last week? We're going to take a quick, closer look to that plot to understand what it means, to make some final recommendations, and then we're going to submit an actual assembly job. All right, you ready? Your build box? Okay, cool. You're ready now. So can you just show the plot? That's a multiplicity graph from the Kmer analysis. It's this one here. 17-mer multiplicity graph. You should be able to find it here. For those of you who don't have the graph from last week, remember what we did. Can somebody just tell me what we did last week on Friday to get this graph? And please don't tell me something like, hey, we did Kmer analysis. No. How did we get it? How did we get it? Using R. But what did you use as input? What was your input data? It's a text. All right. That's good. That's the name of the file. Can somebody tell me what kind of data we used for producing this graph? Not the name of the file. The name of the file is indicative of what we used, but what's exactly what we're seeing here? What kind of information we got from the Kmers that is represented there? So what was the first thing we got from the Kmers? Can somebody remember the first thing we got from the Kmer analysis? It was just a table. Yeah, no, I think most people haven't saved it. All right, let's. Yep. There you go. We need everybody to listen. Yep. So
the first value is how many Kmers there is in our sequence.
Exactly.
And the second value is how many times they repeat it.
Yep. So take a look here, please. Do you remember this was the first file we actually produced from the 17-mer count table.txt. Yep. Just take a quick look at this and try to remember what it is telling you. What is the first number, the number in every outline? What does it represent? Because the Kmer, remember that the Kmer is just a string. This is the Kmer. The AATA, CCAA, that's the Kmer. What does the line above each Kmer means? Look at the name of the file. It has a very tricky. It's 17-mer count table. Basically what we've looked is how many times each Kmer appears in my entire library. So the number above each of the Kmers, that's the number of times we've seen them in the library. So that means that the first Kmer, AATA, CAA, we've only seen it once. The second, only once. The third, only once. And so forth and so forth. So we can explore the table, and we'll see that each Kmer has a different count. For example, this one, GTTCD, it has 135 counts. That is, it appears 135 in my 135 times in my library. It was seen from different reads, because each read was divided into smaller Kmers and recorded into this count table. So all we're doing here is count how many times each of these Kmers appears in my library. That's all we've done. Is that clear so far? Yeah, cool. So now the next step we did, we wanted to see how many Kmers had the same count or were seen the same amount of times. How many different Kmers were seen the same amount of times? A very quick way to see this is, for example, I'm going to use a little bit of bash and piping. For example, let's say we want to see what Kmers appeared 5 times. So we just do, this is probably something I haven't taught you, grep, but it's not really important at this point. Oh, so there's only one Kmer that appeared 5 times. If we were to see how many Kmers appeared 25 times, we would see this Kmer appeared 25 times, this Kmer appeared 25 times, this Kmer appeared 25 times, and there's another one. Did I put after? Oh, interesting. All right. Yeah, so that's basically what we're doing. Yeah. What we want to do is create a table, yeah, where we don't care about the Kmer sequence anymore. All we care is about how many times each Kmer has been counted, and then how many times a Kmer that appeared 25 times also appeared. Does that make sense at this point? We want to know how many Kmers appeared 1 time, how many Kmers appeared 2 times, how many Kmers appeared 3 times. I will just generate a table that tells us the number of times we expect a Kmer to have appeared and the number of Kmers that appeared this many times. That's a histogram. What we want to build is a histogram. And that's what we use jellyfish for. We first used jellyfish last week to generate the Kmer count table, and then we generated a histogram of the Kmer counts. That's how we got this file. 17mer sim histo.txt. This is the histogram. And you will see that it only has 2 columns. Remember that we just checked how many Kmers in my Kmer count table were seen only once. So we've already have the count there. In total, over 600,000 Kmers were seen once in my database. How many times, how many different Kmers appeared twice? Over 40,000 Kmers appeared twice in my database. And so, and so, and so, and so, it keeps going. For each number in the left column, it's telling me the number of times I've seen a Kmer. And the number on the right is telling me how many Kmers appeared this many times in my database. So you would expect that true Kmers would appear, most of them would appear around a value that you had already estimated as the sequencing depth. Remember that based on your filtering and based on the number of reads and based on the number of base pairs per read, you could estimate how much sequencing you did. And based on the genome size, yeah, you could estimate how many times over you had sequenced that genome. And we had estimated that you had sequenced it around 666 times over. That's the kind of data you had. That's why most of your graphs had to show from 0 to 2000, because the average was around 666. So now just we wanna see that, because reading this, it's not really useful. Reading it, it's not really useful. We need to plot it and see if we can make more sense of it by plotting it. And that's the next step we did. We use R. Do you remember, guys, that we used R? Yes. And in R, what we did was we imported this document and we simply plotted. And after plotting it, we started playing around with which were the right dimensions to show so that the plot made sense. So some of you use RStudio, some of us use just simple R, and the idea was to first just import it by using this command, read table, then the name of the file, then telling basically just use the read table command with 3 parameters. First, what is the file we're going to read? It's a text file. Second, how we're going to split that file and produce a table. That's what we use the separate sep equal \t. Have you guys all seen where that sep equal quote unquote \t. It's the second after the first comma in the command. You'll see. First is between quotes 17mer sim histo.text, right? Comma, and then you have a sep equals quote unquote \t. Yeah, that \t in bash terms means tab. That's just a tab. That's the way we represent a tab, a tabulation. And that's how we're telling R that every time it finds a tab in the text file, yeah, it will split a line into 2 columns. That's why it's called separator equal tab. Separator equals tab. All right? And the last part, which says header equals F, means false. We're telling it that the first line of the text file that we're reading is not a header. It's not a set of titles. It's everything in that file is just raw data. If you had headers, if the first line of your file had headers, like titles of what each data column means, then you put header equal true. Yeah, but in this case, we don't. All right, that's how we imported the table into R. And then we just explore a little bit. Oh, sorry. Ah, shit. Sorry. It's not tab, it's a space. Yeah, that was my mistake. The separator wasn't a tab, it was a space. And you'll see that you have 2 columns, V1 and V2. Yes, separator is not a tab, it's just space, sorry. Under separator, you just put quote, a space, quote. That's it. That's how we loaded the data into R. And then the next step was simply to plot it. Use the plot command. Plot. You could use T, but let's use T V1, T V2. Let's just plot X versus Y. We're going to use as X, we're going to use the multiplicity, the first column in our file, and as Y, we're going to use the Kmer count, the number of Kmers that appear this many times. Just put enter and you'll have a horrible graph. Right? It just looks horrible. We have to refine a little bit. So what we do is first, instead of points, we use a line. Type line. All right. It looks a little bit better. Instead of having a lot of dots, circles, showing each data point in my table, we're just showing a line that is drawn across all of the data points. Then we just zoom in. Then I'll just zoom in. I'm just playing around here. I'm just guessing at this point. I'm seeing like a small hump here, so I'm going to show only this spot here. I'm going to zoom in. Yeah, and how do I do that? Using the X lim and Y lim. The X lim, I'm telling you to show me only from, in coordinate X, from 1 to 100. So it means from here to here. And in coordinate Y, I'm telling it to go from 1 to 1,000. Should be here to around here, I guess. Right? That's what we're doing. Yeah, we just press enter and we're going to kind of zoom in. So 1,000 was way too little because you can see that the peaks go all the way above 1,000. So we just use here 5,000. Yeah, it looks much better. So do you now remember how we got to this point? We're just zooming in into that graph, that multiplicity graph. We're just zooming in. What I'm just going to do, just for the sake of making this graph even more readable, I'm going to add some label. It is more spread. You probably have a lot more multiplicity, so you should use xlim from 1 to 2000. You should probably plot it using xlim from 1 to 2000. The ylim shouldn't be an issue. Please, guys, remember that if you don't see anything, it's probably because your data doesn't fit what we're looking. If you want to know what are the best parameters for it, let's do something very quick. Use this quick. Hello, guys. I need your attention for a second. If you're having trouble, guys, just for 2 seconds, your attention here. If you want to know what's the best limits to use in xlim and ylim, please write that command there. Summary. You will print a summary of your table. In this summary, it's going to show you what are the minimum and maximum values that you find in your data for each of the columns, for V1 and for V2. V1 is going to be your x-axis. So look, in my case, it goes from 1 to 291. In V2, which is my y-axis, it goes from 1 to 668,782. Yeah. Don't worry too much about the y label at the moment. Yeah, because remember that the y value is going to give me the number of Kmers. The maximum is going to be the number of Kmers that appeared once, which we all know that they are very likely mistakes. Yeah, so we're going to zoom in into the y label later. But the fact that you choose a correct x-axis, for example, in my case, from 1 to 300 should be all right. Yeah, that's the same thing you need to do. First, choose your x-axis. You'll see that compared to my table, which has a maximum under 291, yours should have a maximum around 2,000 something, or maybe 3,000. Is that correct? So everybody was able to take a better look at your data with that summary table. I've seen that some people here have done a different kind of counting and a different kind of filtering. Some of you only have one. Okay, guys, if you're already here, are we already here? Please, we need to move forward fast, right? If we're already here, this is the most important part of the interpretation. What does this mean? What does this graph actually tells us? It's very nice to plot it, yes, but we need to get some information from that. What does this mean? Any guess is good at this point. Does anybody want to guess? What does this graph mean? The x-axis says multiplicity, the y-axis says count. We know we're dealing with Kmers. We know that the first thing we did was count how many times every Kmer appeared, and the next thing we did is we generated a histogram that we want to know how many different Kmers appeared once, twice, 3 times, 4 times, 5 times, etc. Right? Now, that number, the number of times a Kmer appears, is called multiplicity. And the count on y-axis is the number of different Kmers in my data set that appear this many multiplicity times. So that means, for example, that this huge peak that appears in 1, multiplicity 1, is telling me that basically over 600,000 different Kmers were seen only once in the database. Only once. And we've already discussed this. Usually, when you have a sequencing error, the chances of the same sequencing error appearing twice or more in a sequencing experiment, it's very low. So every time we see a Kmer that appears once in the database, we know we should be pretty sure, yeah, that this is a sequencing error. So all of these Kmers that appear in this peak, this line that looks like a vertical line here, and that if you remember your original plot before you zoom in, yeah, you had a huge line coming from 1 and dropping all the way to 2 and to 3 before you get these nice humps afterwards. That one represents the number of error Kmers that appear. This is going to be important for later on, yeah, but let's keep going. So then we see that there is a huge drop. All right? There is a huge drop from 1, and it keeps low until we start reaching around 50. Or in your cases, in some cases, it will be around 500. Right? Or even after 500, perhaps 600 or something. Yeah? What it's telling us is that from that point forward, more and more Kmers are count this many times. So for example, here, how many Kmers are count 50 times? We just do a vertical line here, and around 1,000 different Kmers were counted 50 times. Then here, we go all the way here. It would be around 57, 55, something like that. Yeah, it appeared nearly, there were nearly 5,000 different Kmers that were counted around 57 times. This is basically telling us that most of my Kmers that are not errors are being counted in this area. Now, if we assume that these are errors, and we should be correct assuming that, then what are these? What would those be? Those would be the true Kmers. Those would be the real biologically relevant Kmers. All the Kmers that appear in this first peak, they should be the real biologically relevant Kmers. Those belong to the actual genome that we're trying to sequence, to assemble. And if you see, the peak should appear more or less around where you estimated your depth would be, your sequencing depth. Do you remember that we estimated the sequencing depth only based on the total number of reads and the total number of bases that were sequenced that you had in your library? We did all this multiplication example. We say, okay, I have 1 million reads. Every read should be around 100 base pairs. Therefore, I should have 100 million base pairs sequenced in total. If the genome size is 155,000, how many times have I sequenced that genome over? And just a simple division. Now, the 100 million divided by 155,000, and you go to around 666,000. Yeah. In some cases where we've done a very shallow trimming, you will see that your peak approaches that 600 number. When we've done a more thorough trimming of the data, for example, in my case, the number reaches around, it should be around 60. Yes? Like this? Okay. So do you have any questions so far? If there's anything that is not clear, please don't hesitate. Ask it around. Juan? You want to ask something? We're gonna get there in a second. Yeah, but yeah, is it clear now? So let's see. If most of my true Kmers are here in this peak, what would the secondary peak mean? Just let's think about the interpretation as it is. Yeah, we're saying that there is a secondary peak of Kmers that have been counted from 100 to 150 times. That's pretty much double this amount. So basically, we're saying some Kmers have been seen twice as often as the original ones, as the ones that we considered true Kmers, the true genome Kmers. Why would that be? Why would I have some Kmers that have around 120 multiplicity? That is, that have been seen around 120 times. Or in your cases, it should be around 1,200 in some cases, 1,300. What feature of a genome would cause some Kmers to appear twice as likely or twice the time that the other peak? Repeated regions. If I have a region that is duplicated in the genome, it's twice, that means that the Kmers produced there are going to appear twice as often as the ones that are single copy regions. Because when sampling from the genome, I don't do a simplification step of the genome. I don't remove repeats from the genome. They are there. So when we start sampling through sequencing and then sampling through Kmer decomposition, yeah, the Kmers that appear in a duplicated region will be counted twice. There's no way around it. And it's good for us to know. Because now we know that we have a region of the genome that is, okay, we have a region of the genome that is that is duplicated. That may cause some issues later on, because duplications are difficult, or repeats are difficult to handle by some assemblers. So now we're going to the assembly. So we already have some understanding of what kind of data we have here. There's a lot more to see, but we'll have to discuss it later. We are running out of time, and I'm taking David's time. So right now what we're going to do is our first assembly command. Some of you may have already done assembly before. Yeah, but this is very straightforward. It's not so much about assembling a genome, the difficult part. It's assessing if the genome was assembled correctly or not. That's the trickiest part. So we're going to leave R for now. Yeah, we're going to concentrate on the data we have here. And we're going to create a new file, a new directory next to INEA05 called test2 or assembly1, whatever you feel like. And you have to zoom in. But we're fast forward that. You need to quit R and create your test file under my documents. Created the test file? Yeah, you need to create mkdir test or mkdir. Oh, you've already created this one. Okay, so what we're going to do is we're going to unzip the assembler. I've already given you under INEA05, there's a directory called INEA space that finishes in a .tar.gzip. Yeah, that is a compressed file. What we're going to do is going to extract it into a directory that can be extracted to. So basically what we're going to do is tar. This is a command to extract tar.gzip files. It's tar xvf. It's just to let you know. XF. Are we all here? Yep. Where are we going to, what file are we going to extract? We're going to extract from INEA05 space.tar.gzip. Oh, I'm just tabbing it. That's the right name. Yes? Remember that you don't have to write the whole thing. You can tab for autocomplete. Just put the first few characters and you'll tab it. That way you reduce the chances of a typo. But it really doesn't matter. It's neater that way. But Don't worry, it's fine like that. It's fine like that. It's going to work. Remember, you can use autocomplete to avoid typos. Typos happen all the time. All right, have you all unzipped? Basically, that tar command, tar, exef, ini, etc., that is to unzip a directory. If you see, once you run this, you will have a directory called space 313 0 Linux. And if you do cd into it, you will see that you have two subdirectories. One of them is called bin. Bin is the keyword in Linux. Bin is the keyword to tell you inside of this directory there are executable programs. Programs that you can run. And you'll see that you have a lot of programs here. A lot of programs. That's because space is one of the most the newest, the most modern assemblers. It has some of the best code for assembling. It has some of the most optimized routines for assembly. Yeah, the algorithm in space is based on a special kind of debridging graph, one of the many types of debridging graph, but it has two main advantages. First, it uses very low memory print. That is that you can economize your RAM. You can put it a limit of how much RAM you want it to use. And second, it's because it builds a debridging graph based not only on one Kmer size, but on different number of Kmer size. You can use as many Kmer size as you want. And what space is going to do is going to build the debridging graph iteratively. First with K6, then with K7, then with K15, then with K17, then with K27, and as many as you want to give it to it. Remember, the bigger the Kmer, the more RAM you're going to use, the more Kmer sizes that you want to give it to it. Yeah, it's going to be more time consuming because you have to repeat the assembly from scratch. But the nice thing about doing that is that it builds a multi-K debridging graph. That is a debridging graph that has different Kmer sizes, and therefore it will produce a more correct assembly. So now we're going to run it. If you want to know how to execute a space, you just have to do this. // is when you're telling the bash, hey, we're going to execute something. All right? / is us telling bash, we're going to execute something. Yeah, it would be better if you jump closer. Then we select the program. What is the program? We just saw it. It is a space Linux bin space.py. If at this point you just press enter, you're going to get a help. If at this point you want to add -- help, you're going to get a help. That's the first thing we do when we try to execute a new program that we've never executed before. -- help, yes. All right, so some people, and most of you have asked me the same question. So I'm going to talk about this a little bit. It's a bash thing, it's a Linux thing. Essentially, Linux has a way of knowing what are global installations and what are local installations. All right? If, for example, let's think about this. Yeah? Let's say you're all working on the same place, yeah? And you have a designated parking lot. All right? So you know that all of you have a car and you all always park it in the same spot. But then a new guy arrives, he's just been hired, he doesn't have a spot there, and he parked his car somewhere else, outside of where you usually park it, right? Yeah? And the guy approaches you and tells you, hey, can you go pick up my car, please? Here are the keys. How would you know where to find that car if he doesn't tell you? You don't. You don't know where to start. That's the same with Linux. If you install a program in a random place in Linux, Linux doesn't know that that program is there. You have to look for it. But Linux has a set of directories that are commonly used for global programs. So for example, Spade is a program that you just brought in. You copy it, you unzip it, and you put it on your documents directory. How is Linux supposed to know where it is, that it is a program or anything? It doesn't know. If we had chosen a directory that is one of the default Linux directory for programs, then wherever you are, you just type spades.py and it's going to run. But in this case, we haven't. We just unzip it on one of the directories. That's why we put the full path. That's why we tell the Linux, hey, look for the program here. And that's, for example, some cases you just have to put a spades, bin, share, and spades.py, because Linux doesn't know where the program is. But if we have copied the program over to a place that we know it's going to have, that we know it's going to work, that Linux knows it's where it stores executables, then Linux wouldn't have had any problems with that. Yet, we're not diving much into it because that's a whole different subject. But so far, the most important thing is that if you're in a directory and you remember how to reach the spades zip file, the spades that you have just uncompressed, you probably did it on documents. So if you're in documents test, you put // to go back one directory. Now you're in documents. Then you put spades tab so that it completes, and now you're in spades. And then you put bin so that you go into the binary directory, and then you just spades.py, and you shouldn't have any issues just getting this help. So everybody is on the new directory that you've created, spades. You can call it test2, you can call it test, you can call it assemble, you can call it whatever you want. Just remember that you're under documents, and the name of the directory you created. Okay? Now, you will have to use a lot of memory. But just remember that your data, your trim data, is on INEA05. That's where your trim data is. And your program is on wherever you unzip or uncompress your spades folder. So, we're going to need some commands. First, we need to put, to tell, hey, where to find spades. Yes, just like you got the help, using the same command you used to help, write the same but don't press enter. If this is just to select, this is the program I want to run. We're going to add more things to this thing. So if you see the help of spades, it tells you that it just requires, well, obligatory just one thing, an output directory. So that's the first thing we're going to add. -O and an output directory. Remember that the output directory is, well, let's just call it a spades or a spades test. Yeah? And that's the first line we're going to add. So we're going to put it like this. All right, everybody's here? So you know that the first argument to this spades command, spades is an assembler. All right? Your attention, please. Your attention, please. We need to wrap this up as fast as possible. So the first argument you have to give is the output directory. You can create your own name, but please remember where you are. For example, I'm here in document test too. Yeah, remember where you are, because wherever you are, that's where the output directory is going to be created. If you're in documents, you're going to have documents / and the output directory you're giving. If you're in INEA05, it's going to be INEA05 / and the directory that you're creating. Yeah? If can you wake him up? Yeah, no, it's from the outside, yeah. So please be mindful of that fact, all right? Now, the next thing we need to do, let's look at the help. It says, after you select the -O output directory, again, you can check different different flags. For example, --SC is required for single cell data. Do we have single cell data? No, so we don't use it.
All right. So ion torrent. Are we using ion torrent data? This is another sequence here, and it's out of fashion. Nobody uses it anymore. No, we don't. --test. Run spades on a toy dataset. We're kind of doing that, but spades has its own dataset. We're not running that one. And now the next one, it's file name. Yeah, you can use --12 if you have one single file with both forward and reverse reads. We don't have that. But we do have is one file with the forward parent and another file with the reverse parent. That's what we do have. And now we have to remember where they were. Do you remember where they were? On INEA 05. All right. So that's the first thing. First, we're going to use -1. And where am I? I'm on test 2. So I'm going one directory back. That's what the two dots / are for. We're going one directory back from test 2 to documents. Then we go to INEA 05. And then I look for my simulated data 1, and I have a trim. Trim.fastq. That's it. All right? I just remembered where my trim data was, and that's the one I'm going to use. The spades -O, spades assembly, -1, which is telling the assembler A. This is the first paired, the forward reads are going to be in INEA 05, sim1, trim.fastq. Do you remember, did you create that document? Yeah. Tab it. You have all these options. Trim. Do not press enter. By the way, do not press enter yet. We're just filling in the command. The command is much larger than this one. If you press enter right now, you probably get something running, but it's probably gonna be an error. All right. So this command is not complete. So don't press enter yet. Okay. Now that you've all completed the -1 and put the first forward reads in there, now you have to do it with the -2. It's the same thing that you just did. It's just that now we're telling the spades assembler, hey, these were the first read, now these are the second pair of reads. These were the forward, now these are the reverse. Because remember, we're working with paired end reads. 2 pairs for each template. So what we do is the same. -2, space, and just remember where you kept your... Now we're using sim2, because this is the second pair. We're not using the same file as before, we're using sim2. And don't press enter yet. We are here. We are here. -1, -2, file name. If you had several different libraries, you could actually put -p1, -p2, -p3, -p4, etc. Yeah, and just complete for all these libraries. These are just repeats of the same, of different kinds of library. And for numerous libraries. So if you had Sanger reads, you could also add them to the assembly. If you had PacBio reads, you could also add them to the assembly. If you had Nanopore, you could also add it to the assembler. If you had previously built contigs from another assembler, you could add them here. If you have a list of trusted contigs, that is contigs that you know are well assembled from a different experiment, you could add them here. Right? So all of these you can add in this space. It's a more advanced use. We're just going to do the basic one. So let's just keep going. Pipeline options. So what parts of the pipeline you want to run? Do you want to run only error correction, which is the first stage? Yes, no. Do you want to run only the assembler? Yes, no. We're going to do both, error correction and assembly. So that's the default behavior. Do you want it to be careful when building the contigs or not? This is going to fine-tune some of the internal parameters to tell them just keep contigs that you're absolutely confident that are contiguous. If for some reason your assembly was interrupted at some point, a power outage, your battery died, your computer died because of RAM, the cluster you were running it in just had a major power failure and it just killed everything, then you can always use a restart or resume. Yeah, restart from will tell you from which stage you want to restart it. From error correction, from assembly the first Kmer, from assembling the second, the third, the fourth iteration, etc. Disable Gzip output. Basically, you want your final results to be zipped, to be compressed or not. Ideally, in this case, we don't need it to be compressed. And disable RR, repeat resolution. This is what we're telling, what we were saying. Attempt to solve repeats based on error information and based on the sequence length. If they can do it, they will try to. But if you want to skip the stage and don't let the assembler to solve repeats, then you just activate this. We are not going to activate this. Yeah, and then here are more advanced options, but these are just regular, for example, dataset. This is just a description of the dataset. If you have like hundreds of libraries that you want to add, you can add them as a YAML format, which is something we're not going to even touch today. You can select the number of threads. This is something we might want to use to speed it up. So -T, 4. I have 8 threads in total in my laptop, so I'm going to dedicate 4 to this. Yes. That's true. You have to use this one because by default, Space is going to try to use 16 threads. Our computers, neither of them has 16 threads. Yeah, you probably best case scenario you have 8. Yeah, so and that is if you have 8, that means that at least one thread is using Windows, another thread is using your VirtualBox, another thread is probably opening the command line, and another thread is probably using the directory, the visual directory. So you have to be careful. I would say just use 4 if you have them. If you don't, just use 2. Yeah, memory. How much memory to allow a space to grab? In my computer, I have 8 gigs of RAM. Yeah, each of you will have a different amount of RAM. Yeah. Please don't let it exceed 1/3 of your RAM. Yeah, that means in my case I can go up to 2 or 3 gigs of RAM. Yeah, but thank you. Yeah, that means that I can use 2 or 3 gigs of RAM. Yeah, but if you only have 3, please don't go beyond 1. In my case, I'm going to just use 1 gig of RAM. That was enough last time. -M, 1. Here, it's just an integer. Temporary directory, if the program needs to spill things into disk, that is, if there are some files that it needs to save temporarily, yeah, where to write them. Yeah, in this case, the example is too short to actually generate temporary files, so you don't have to worry about this. -K, this is essential, but we're not going to use it because it has defaults. Yeah, this is the list of Kmers that we're going to use to generate the debridging graph. Yeah, that's the size. Just as we did the 17-mer exercise just to do the Kmer analysis, every debridging graph requires a Kmer size. In this case, it requires a list of several Kmer sizes. By default, it will analyze your data and will select the most appropriate Kmer size by default. But if you want to override that decision, yeah, that the program makes on your behalf, you can do it here. You can tell it, yes, I don't want to use the default ones. I don't want to use whatever the program recommends. I want to use my own list of sizes. So we could do it. Yep. We shouldn't at this point, but we could do it. At least you have to put 3 Kmer sizes. If you want to use this, at least you have to put 3 Kmer sizes. Yeah? And they all must be odd numbers. Just as we discussed last time. They have to be odd numbers in order to avoid palindromic sequences in the Kmers. So I'm gonna skip this for now.
Yeah, but this is a very important a very important part of every debridging assembler. Select the Kmer size. Finally, a coverage cutoff. That is, do not assemble contigs that have at least, in this case, that have more than this coverage in total. That is, how many reads are aligned to each position in the contig. If the coverage is way too high, then that means that you have a severely repeated or contamination in your data. So that's something you don't want to assemble. But this can also be estimated by the program. We could also estimate that from the Kmer graph we did before. We saw what was the maximum size, or around what sizes we expected the multiplicity to be for real Kmers of the genome. And we saw that there was a repeat, like a smaller hump farther down the road, around 120 coverage. Yeah. So that's what we would expect to be correct. If we have Kmers that appear 1,000 times, that's probably either contamination or transference RNA or some region of the genome that it's just crazy repeat. Yeah, that's something that the assembler is not going to be able to handle well. So we just skip those. The Fred offset is like we talked about last time. It's what kind of quality encoding is using. Is it using the 33 ASCII, the Fred 33, or is it using the 64 ASCII, which is Cassava 1.5? It's a whole different. Just keep it on 33. It's the default. Yep, that's it. That's basically it. If you want to use the -k, you can just put here 27, 37, 47, for example. Something like that. Yep, if you want to use it. I recommend not to use it at this point. Yeah, this is just an example. All right? So once my command is ready, now I can press enter. Some of you may get errors because there might be some typos. Or there might be some files that cannot be found because of a typo or because you're in the wrong directory to find them. Yep, just be patient and remember, those are the most common errors. First, check if there are typos in the names that you're using. If there are not enough spaces, check that you're not quoting or anything like that. Yeah, and the other thing is that if you have an error that says file doesn't exist, please read your errors to know what's wrong. Yeah, if they said file doesn't exist, that means that you have the wrong path to the file. So you have to double check where you are and where the file you want is. Now I shouldn't have any errors. There we go. It's running. If it's running, it should look something like this. Yeah, it's telling you everything it's going to do. So for all of you who have already finished your assembly, yeah, you can see that if you double L, yeah, you will have the directory that you wanted to create. It's already there. Yeah, the directory that you put as in your command line, -O and a directory name. Yeah, in my case it was Spades assembly. It's already there. So you can CD into it, and you will see a lot of files and directories. So first thing you'll notice is that there is a spades.log. That's the last file I was reading. Yeah? My recommendation always start looking into the log. Or if there is a README file, you should also start by the README file. But in the case there is none. So start by the log. You use either Nano or you use Vim to look into spades.log. It is a big file. We're going to see that basically everything that we saw running on our screen, yeah, it's copied into here. Every single line. And it tells you everything. What version of Spades you're using, what version of Python you're using, what operating system you're using, what's the output directory name, what kind of mode we're using, read, error correction, and assembling, if you're using a debug mode, where all your files are, left reads, right reads, here. Dataset parameters, if it's multi-cell, library number 1, left reads are here, right reads are here. Now we keep moving down. You'll see what assembly parameters we used, the Kmer size that we used, 27, 37, 47. We ask him then all this stage by stage, step by step of the algorithm, how much RAM it used, where it was run, what was the program running, and what it was doing. Yeah, so we can skip that. If you're on Vim and you want to go all the way to the end, just Shift G. If you're on Vim and you want to travel all the way to the end of the file, just Shift G. And this is the end of the file. It tells you, the assembling finished. It used Kmer sizes 27, 37, and 47. And it gives you the list of what are the important files to look for. First, the corrected reads are in test2 Spades assembly. This is the output directory that I put, / corrected. The assembled contigs are going to be in the Spades assembly directory, contigs.fasta. The scaffolds are going to be in scaffolds.fasta. The assembly graph is going to be in assemblygraph.fastg. This is something we haven't talked about. It's another representation of an assembly, just in kind of a graph format. The assembly graph in GFF format, which is another graph format, is going to be assembly graph with the scaffold.gfa. We're not going to look into that. But if you want, if you're curious, you can just head or tail or Vim, and you'll notice that it's just a text file. It's just, all of these are just text files. You can just look at them, and you should have no problem seeing what's in there. Path to the assembly graph corresponding to the contigs are here. These paths, these are probably binary paths. So you won't be able to read them straightforward. And for the scaffolds are here. So we're going to see that we want to start with the contigs. The contigs are the ones that we're interested in. We don't know if the scaffolds were done correctly, so we're going to start with the contigs.